Welcome to Chemistry. This is a presentation for Chapter 1, Section 1. This is a narrated presentation. This effectively, for Section 1, is the classroom presentation, however, with narration. And this is intended for students who are absent, who are quarantined, who are doing any work online, and participating in Chemistry 1 at CV High School. So let's move on. This slide here is simply to indicate that our chemistry classes, like all science classes at the high school, are standards aligned with the Pennsylvania Science Standard appropriate to that particular class. This is simply a subset of some of the standards that apply to our particular chapter and our set of topics that we are covering. This is by no means a complete list. All of these topics and more will be discussed further in these slides and the other two presentations, which will make up the rest of Chapter 1. Okay, Matter and Change, Chapter 1, Chemistry as a Physical Science, I believe is the name of the section out of your textbook, and this does correspond with Section 1 material. I will say that in my presentations, on occasion, there is material that is presented that is not necessarily in your textbook, but I have felt that it is information that is good to know that aligns with the topic. We will always be filling out student learning maps for all of the chapters that we cover in Chemistry 1 and Chemistry 2, as a matter of fact, and to all sciences at the high school. And as you fill out your student learning map, the key learning is always a statement, whether it's a complete statement or simply partial statements. In this case, the key learning is the definition of chemistry. What is chemistry? It is the study of the composition and the structure and the changes that matter will undergo. And because all change involves energy, we are going to put the term energy involved during change within this particular definition. Depending on where you find the definition of chemistry, it may or may not mention the component of energy. However, I have felt that the definition without employing energy is somewhat incomplete. When you look from book to book, from website to website, from dictionary to dictionary, if the definition of chemistry changes, it is because it is either more specific, more detailed, or it is more general. This is a definition after years of looking over definitions. I have landed on this one, and I felt that this particular definition of chemistry really captures the essence of the entire course that you will have, and really the science as I know it. Now, the unit essential question is how and why do chemists classify matter? Because chemists study matter, and matter is essentially everything around us. And when I say everything, that is in all caps, everything, with the exception of forms of energy, which are not made of matter. So that is a huge, monumental task as far as how much matter is out there. So there needs to be a way to classify it, to simplify everything that is around us. And so the question here is, how and why do chemists classify matter? This particular question will be on your test. And as a matter of fact, in all of our chapter tests, the unit essential question will appear there. Now, this is unique to Chapter 1, so this will be on the Chapter 1 test. In the Chapter 2 test, the Chapter 2 unit essential question will be there instead. In your student learning map, you would also want to include the concept. This is the first lesson for Introduction to Chemistry. And here the lesson question is simple. What is the definition of chemistry? Coming out of the first lesson, the first section. If you can do that, you're doing well. The objectives for this particular chapter and this particular section specifically are these 5 statements. Now notice these 5 statements, and I do have an interactive pen, so let me go ahead and come up and do this here. So with these particular objectives, contrasting physical and life sciences, defining chemistry, restating the law of conservation of mass, sometimes called the law of conservation of matter, and either word is okay, it's the same law. Listing examples of the branches of chemistry, of which there are 6, and both comparing and contrasting. How are they alike? How are they different? 3 types of research, and in fact there are actually only 2 types of research. There is a third item on the slide that mentions research, but that third item is actually how technology applies. It's not a type of research, it's actually just a mention of technology, so that's incorrect. Now, in all of these objectives, I would have you note that there are no actual stars, like an asterisk. Okay, so there are no asterisks here. And if there was an asterisk, that would indicate that that objective has been significantly changed from one out of the textbook, or I have added an objective completely that is not in your textbook at that point. So whenever you see these objectives, a couple of things should apply. One thing you would want to know is that these are my source of test questions. If you want to know where the questions come from, here is where they come from. I can take any one of these 5 or all 5 of these and turn them easily into test questions, and that's what I do. So cat's out of the bag. There's my secret. There you go. So you really know a good sampling of test questions, because if you look at all the objectives in the chapter, there you have it. Pay attention, though, specifically to anything, again, with a star. If it has a star, it's not in your book, and you'll really want to make sure that you focus on that or you record that one down. Okay, moving on. Physical and life sciences. So chemistry is a physical science, just as physics is also classified a physical science. And of course, you can see that they both study aspects of the physical world, and they do analyze nature using the scientific method. As contrasted with life sciences, which of course are very concerned with studying of life, of living organisms, past or present, alive or dead. Life sciences, there are many life sciences, many fewer physical sciences, unless you get into like the subcategories of chemistry and physics. But this is the difference. The only other science that is not up there is earth science. That is actually considered a third main branch of science with its own subdivisions. I did not bother to put it down on this particular slide, but it is a third branch. Okay, this is a very important slide right here because of the content, certainly. And that is, first and foremost, the definition of chemistry, and then the definition of the law of conservation of mass. Now, for note-taking, I'm okay with using the abbreviation LOCOM, LOCOM, if you will, like an acronym. But for testing and formal purposes of homework, you need to spell all of this out, law of conservation of mass or law of conservation of matter. So chemistry. This definition will appear actually on your test. It is a test question. In fact, it's not only a test question for Chapter 1, but it's actually a test question for every chapter test. I'm a firm believer that you understand what the class is about. I know early on you will memorize this, and it's just kind of rote memorization, and you can put it down without ever thinking about it. However, eventually, I will need you to think about this definition and what it really means and how it is going to actually apply to various topics as we go through this course outside of Chapter 1. So what is the definition of chemistry? It is, of course, your key learning on your student learning map, but here it is. Chemistry is the study of the composition and structure of matter, the changes matter undergoes, and energy involved in change. This is a 4-part definition, and on a test it is always worth 5 points minimum. 4 points for each component and 1 point to tie it all together into a coherent grammatical sentence. I do have a lot of students that will say, oh, chemistry is the study of chemicals. So what is a chemical? Well, a chemical is simply any substance with a definite composition. This would be like salt, sugar, which is C12H22O11, which is table sugar, by the way, water, H2O, and it goes on. Just gold, AU, or I'm sorry, that's silver, AG, or gold, AU. All of these would be chemicals because they all have fixed compositions. However, something like sand, like a bucket of sand, is not a chemical. The reason why is because sand has a varied composition. From 1 teaspoon to the next, the composition would be changing for a bucket of sand. So that's a chemical. However, chemistry is way more than that. So please make sure that you get this class definition. I will be expecting it. Certainly you can paraphrase this definition. I do not encourage that because I found in most cases paraphrasing some of the definition gets lost in various word changes. So simply be careful with that, and if you feel strongly about paraphrasing, see me, let me know what your paraphrase is, and I'll tell you if it's going to be acceptable. And a 5-pointer, is it a 5-pointer paraphrase? The law of conservation of mass on a test will also be asked every single test. and it is also 5 points. So now you know 3 test questions specifically that will be on every test. One is the definition of chemistry, one will be restating or defining the law of conservation of mass, and the third one is always the unit essential question, which changes from chapter to chapter to unit. So the LOCOM, the law of conservation of mass, is also a 4-part statement and a 5-point question. So what does this say? The law of conservation of mass states that matter can neither be created nor destroyed by ordinary means. You don't even need this word chemical if you don't want, just by ordinary means, but it can be rearranged into new substances. So there's your 4 parts. You can't create it, can't destroy it. By ordinary change, all you can do is rearrange it. And this underlies all of science, and it's certainly very, very surface level application. It underlies chemistry in that it applies to many of the things that we'll talk about seemingly on a daily basis. Let's move on. Just a joke. 2 men walk into a bar. One man orders H2O. The other says, "I'll have H2O too." The second man dies. Yes, it's a sad joke. However, as jokes go, this is actually very, very poignant in that when you are talking about H2O and H2O2, H2O2 is hydrogen peroxide. And so this really, as much as it might be just kind of an off joke, science jokes, what can you do with them? Most of the time they're not really funny unless you're just a diehard scientist. But in this particular case, I like the joke in the fact that it is really emphasized both composition and structure. 2 parts of that definition where water and hydrogen peroxide are only different by 1 oxygen, but the difference is significant in that water, you drink it, you wash your hair with it. Hydrogen peroxide, you drink it, you get sick, you drink too much, you die, and if you wash your hair with it, your hair gets significantly lighter. And so I like the joke. Let's move on. 6 branches of chemistry. In your book, you'll be able to read about the specifics on each branch and a definition. Organic chemistry, which by far is the largest branch of chemistry out there, and it is a branch that is still growing even yet. So it's a large and it's getting larger as far as organic chemistry goes. Organic chemistry is primarily focused on the study of carbon-based compounds. So one element, carbon, and all of the compounds that carbon can make, it is literally that grand of a number. It's millions upon millions. And so very important. We have an entire branch of, well, the largest branch of science, of chemistry rather, that is actually dedicated to the study of carbon. Inorganic chemistry is the study of everything else except for carbon. Now, carbon may be in a few things that we study in an inorganic setting. However, it is primarily focused on everything but carbon. And that's in the hundreds of thousands, maybe, just maybe a million, but certainly by no means millions upon millions. So inorganic. Our particular class, so our science class, let me say this, our class is an inorganic chemistry class, because in there you'll get all of the various foundational material that apply to all chemistry branches. Then there is physical chemistry, which is primarily involved in understanding how matter and energy interact. Analytical chemistry, primarily concerned with the makeup of materials, like finding out what materials are made of. Biochemistry is certainly where biology and chemistry significantly overlap, and so you're going to be looking at chemicals involved in life processes. And then lastly, theoretical chemistry, which is primarily concerned with the design of new compounds, new chemicals, and new chemical processes, maybe to make old compounds, but we want to make it through a new process, a better process, a more economical, a cleaner process, a process that pollutes less, costs less, etc. You see what I mean there. Okay, research. So there are 2 types of research. There is basic research, which is simply research undertaken because we are curious. And this research has been around ever since people wondered why. If they had a question in ancient times and they sought an answer to that question about something around them in nature. This is basic research. And certainly it's way more formal than it was back then, but that's what it is. You know, like for instance, my question here is, it's very interesting that a lightning bug can light its butt up. I mean, man, how cool is that, right? How can a lightning bug light up, but there's no heat there? You know, it doesn't get burned, but it can light up and continue to light up all night long and do it night after night. That's interesting, but you know, there's nothing really there other than curiosity. And so that would be basic research. These days, for the past 100, 200 years, we've really been involved in a lot more applied research, which is really research that is attempting to solve a specific problem, like air pollution, like a disease, like cancer, or my goodness gracious, COVID-19, the coronaviruses. So when we have a specific problem and we undertake research in order to find a solution to that problem, that is applied research. And applied research over the past 100 years or so generates money, because when you find solutions, oftentimes you can sell those solutions and make money, whether you're a university with a lab or whether you're a private industry with a lab, whatever it is. You can be willing to bet that the company that figures out the vaccine for the COVID-19 virus will be wealthy by the time they get on selling that vaccine. It's just the state of the world economy, actually. But that's applied research. Now, in all of this, and this is not research, technological development, things that we discover through basic research and applied research, we make a lot of discoveries besides the answer to the question or the solution to the problem. Things that we discover often end up being able to are able to be applied to some sort of technological development. We knew about electricity long before we put together a calculator, but eventually, you know, once we understood the ins and outs of electricity and circuits, we were able to make a calculator, and everybody's phone these days has a calculator on it besides every, you know, the 101 other things that it can do. Some examples would be chemical lights, like the 4th of July glow sticks. You know, you break the little ampule inside, shake it up, and it glows for, you know, 4 hours, 8 hours, 24 hours. Cars, dishwashers, robots, computers, pencils, for goodness sakes, are technological developments once we understood about how to make a pencil, even though that's relatively simple as far as technology. So to M or not to M, to measure or not to measure. Chemistry, certainly, like every science, and I mean every science, chemistry is a quantitative science. That means that chemistry is backed up through measurement. We establish our facts, what we know, because we are able to measure it and remeasure it and consistently measure it and reproduce it. And so we know 100%, 95%, 98%, whatever that high percentage is, that we know what we're talking about, that we can measure it and you can measure it and we're going to measure the same thing. So whatever it is, it's based upon quantitative observations. These are measurements that, these are observations that are made through and by measurements and calculations of those measurements, and we consider these fact, and they help establish our concepts and our understanding of the world around us, and of course in this case through a chemical lens. As opposed to the other type of observation, which is called qualitative. So quantitative, measuring. Qualitative, no measurements. These are observations which are simply made without measuring, and these observations are disputable. So you look at this particular slide and you see maybe a blue background and white lettering, but I see a yellow background and green lettering. Okay, so at the moment, you know, so well, you're going to say, man, you're just being silly here, but prove me wrong. Prove to me that that is not a yellow background and that's green lettering. Well, you can't, because you have no ability at this moment, I'm assuming, to measure what color is actually the background of the slide other than your eyes, and that's not a measurement, that's just a qualitative observation. And so until we can measure it, we can dispute all day long the color of this slide and the color of the writing on the slide. It's that idea which is a qualitative observation. Now, qualitative observations made by a competent observer are reliable to a point, and they do have a place in science, but really we want to be able to measure things. So how could we prove the color of the slide? What we could do is actually we could measure the light that is absorbed that gives the color of this slide its color. And we can use like a spectrophotometer or some other light capturing device, and we could measure what's absorbed and what's reflected. And so we would be able to prove exactly what the wavelength of the light is, and therefore we can align it to a name of a color that we have chosen. So we could prove what color it is to a very good degree, but we can't just do it with our eyes. We're going to have to measure it with a device. Historical chemistry. Well, chemistry goes way back a long ways, even before alchemy, which comes from, and I'm going to unfortunately butcher this, but I believe it came from an Arabic term, alchem, if you will. And that term becomes alchemy, and of course eventually becomes chemistry to us. But alchemy is just an ancient form of chemistry practiced probably during the Middle Ages and before. Some of it came out of the Middle East. Before that, before the Dark Ages, it was in Europe. And the alchemists really had up to four, if you will, four general types of goals if you were an alchemist, like a court wizard back, in the days of castles and such. So there were secret medieval chemical philosophers. Philosopher was the old name given to someone who mixed they were philosophers, yes, but they were actually scientists. And who tried to do what? Well, of course, the whole turning lead into gold, or turning really anything into gold. So that's turning something into gold would be officially called transmutating. So transmutating substances into gold, because gold was considered very pure and, of course, valuable and rare. They wanted to also create what's called a panacea, which is a remedy for anything. If you drank this, you would literally be cured of whatever ailed you, from cancer to the common cold to a headache to a toothache to, a paper cut. Create an elixir of life for longevity. So not only could you be disease-free because of the panacea, but if you drank the elixir of life, you would have a long life. Very important when the average lifespan was like 30 to 40 years old, with high death rates after that, back in medieval times. And then lastly, they wanted to be able to create a universal solvent, which is a substance that can dissolve anything if it's universal. No such thing that one substance can dissolve everything, but we have some substances that do dissolve quite a bit. But anyway, the universal solvent. And finding the universal solvent would probably help them with the first three goals. So that was kind of another means to an end. But these are the alchemists. Those are their general four things that they wanted to do. Now, unfortunately, while there was a lot of good science that actually occurred with these medieval chemists, they were very, very secretive, and they did not share their information, because if they shared their information, they would be viewed as less powerful, because it's kind of like a magician that you know exactly how they do all their tricks. It really takes the mystique out of it, and you're not going to buy tickets to that magician show again. So these medieval alchemists, if they gave away all their trade secrets, then they really would not be perceived as having any kind of power, and so their livelihood was taken away from them. And so they were very secretive, to the point of where they would write in code, they would not write anything down, and all of this really died with most of the alchemists. And so what little survives and what little we were able to decode, we realized they were actually doing some pretty good science that died, unfortunately, with them, and kept science held back for a long time. This is the end of Chapter 1, Section 1, and this slide is just telling me that next up is Section 2, which will be a separate video. So there you have it. This is Section 1, and the other presentations, while maybe being slightly interactive, if there's anything to interact with my pen, that I will certainly go ahead and employ that. But otherwise, it's just trying to provide an alternative means for these presentations to really back up what we're doing in class, or if you miss with absences, you miss any days in class, that there is this resource through probably the Google platform. Thank you very much, and contact Mr. Spencer, me, with any questions that you have or any concerns, and we'll take it from there in a class setting. Thank you.